Theoretical physics faces a foundational conflict between the smooth, continuous manifold of general relativity and the discrete, localized entanglement of quantum mechanics. At high energies, the continuous metric fractures as the underlying quantum structures become visible. The Adelic Langlands framework treats spacetime as a non-local field of automorphic forms mapped over an adele ring. The smooth, four-dimensional Einsteinian universe we observe is a low-energy semiclassical shadow, the macroscopic result of a cosmic decompression process that projects dense quantum information into continuous space. A multi-scale entanglement renormalization ansatz, or MERA tensor network, provides the exact discrete architecture for this background. The arithmetic engine of number theory dictates the constraints of our universe, from the strength of gravity to the limits of holographic complexity. Our derivation begins with microscopic spectral regularizers. These filters remove infinite arithmetic divergences to define the finite pixels of the MERA spacetime network. From these pixels, we derive the global logos field action, a functional that governs the non-local quantum state density of the entire system. We then extract the specific, predictive equations required to map these dynamics onto the observable universe. By calculating the precise geometric limits of the adele ring, this architecture generates testable signatures for the cosmic microwave background and for the next-generation dark matter surveys. Constructing these space-time pixels requires evaluating the infinite-dimensional spectral trace of the Dirac operator. Without regularization, this trace produces the divergent mathematical infinities that typically collapse quantum gravity models. A joint spectral projection filter prevents this divergence by applying two simultaneous constraints to the incoming quantum state. The Gaussian Unitary Ensemble, or GUE filter, captures universal statistical fluctuations to screen out chaotic, high-frequency noise. In the tensor network, this functions as a disentangler gate, decoupling short-range correlations before they are processed. Complementing this is the Uniform Density Distribution Projector. It forces a flat, uniform spectral density, operating as a coarse-graining isometry gate that lifts information to higher scales. These projection pixels build the 2D MERA hierarchy. Vertical nodes track primescales, mapping the physical decompression of space as information flows outward. Local Hecke operators provide the horizontal transport rails, distributing entanglement sideways across independent MERA columns without violating gauge invariants. Because the Hecke algebra commutes with the spectral filters, horizontal transport and vertical coarse graining occur simultaneously and smoothly. Algebraic filters process an incoming stream of number-theoretic data to quantize space at the spectral level. Any localized node within this tensor network must have a finite limit on its information density, or bond dimension. We derive this limit by applying the Minkowski convexity theorem to the lattice of arithmetic sections. This produces a rigid upper bound on the tensor bond dimension. The absolute field discriminant acts as the denominator here, specifying the arithmetic quantum of space. It determines the minimum volume required to store a single bit of information. If we attempt to pack lattice points more densely than this threshold, the arithmetic structure itself fails. The Ray-Singer analytic torsion stabilizes this bound at high energies. It functions as a non-perturbative counterterm, absorbing the standard one-loop UV divergences of quantum gravity. Since the maximum entanglement entropy, or S, is the natural log of the bond dimension, this arithmetic capacity formula defines a physical ceiling for local information storage. This number-theoretic cap on tensor entanglement provides the structural resolution to the Bekenstein entropy bound, ensuring that information density remains strictly finite and structured, even at the absolute heart of a black hole. The dynamic evolution of this bounded network is governed by logos field theory. The logos field action functional tracks the global state density across three distinct sectors. The Archimedean sector forces the field to align with the Weil-Peterson metric, anchoring the large-scale geometry of the moduli space. The non-Archimedean sector drives discrete kinetic evolution, where local Hecke operators act as quantum circuit transformations. The interaction potential couples the state directly to the faulting's height, representing the holographic computational complexity required to sustain the universe's configuration. When we apply our spectral filters and take the large N limit, we can vary this action to find its semiclassical trajectories. The chaotic, non-Archimedean fluctuations wash out, leaving the classical Euler-Lagrange equations for geodesic paths. Continuous Einsteinian gravity emerges here as the low-energy shadow of the automorphic field. During cosmic inflation, expanding spatial slices underwent an adelic decompression, causing finite p-adic sectors to freeze out. This decompression left behind a series of discrete fingerprints on the primordial scalar power spectrum. Hecke eigenvalues and primescales drive interlocking, log-periodically spaced oscillations that ripple across the standard cosmic baseline. As the tensor network decompressively expanded, branching events at the tree vertices injected sharp, localized steps into primordial non-Gaussianities. Because the analytic torsion bound prevents the perfect smoothing of the background, the model predicts a definitive lower limit on the tensor-to-scalar ratio of 0.0017. These arithmetic patterns are hidden within the cosmic microwave background. Specialized Mellin Fourier transforms can extract these log-periodic residuals from high multipole data to confirm the network structure. Inflationary history preserves these arithmetically spaced fingerprints, mapping the expansion of the early universe directly to the quantum circuit. Extending the Logos action to include fermonic superpartners isolates a stable, non-thermal candidate for dark matter, the Logosino field. The super-Satake isomorphism splits this field into a discrete tower of mass eigenstates keyed to the prime numbers. Arithmetic dark matter exists as an integrated multiplet of mass states, natively indexed by the Adele ring. Its scattering cross-section is suppressed far below the coherent neutrino floor, placing it beyond the reach of traditional multi-ton WIMP detectors. Its primary signature is indirect, string cusp decay generating a concentrated gamma-ray line comb in galactic halos. Detecting these monochromatic lines, separated by exact log prime ratios, is a primary objective for next-generation gamma-ray telescope arrays. This multiplet structure confirms that the dark sector is an extension of the same number-theoretic infrastructure that builds spacetime itself. Total analytical closure of this framework depends on Beilanson's conjecture regarding the special values of L functions. We establish a direct mathematical identity equating the derivative of the global automorphic L function to the topological Berry phase of the boundary conformal field theory. This proves global analytic information dictates the adiabatic phase shift picked up during the quantum transport of primary fields. The architecture exhibits total logical closure. Analytic torsion cancels UV divergences. Minkowski convexity bounds information. And adelic decompression generates continuous gravity. The definitive validation of quantum gravity lies in the mathematical astronomy of the future, detecting arithmetic residuals written into the sky.